Hi, it's Glenn again with the LateNiteLab calculations for the testing air on gas laws experiment. Here are the calculations for experiment 1. My numbers will be very different from your numbers, but you just fill in the table with your numbers. I'll just fill in 3 points here. Of course, you'll have more points, but just to show you how this is done, I'll just use 3 points. 3 points are just barely enough points for you to draw the graph here. I mean, for me to draw the graph for you here. 259.9 is this number plus this number. Somehow that I forgot to put that in the lab notes. Ha 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 ha. Sorry. So that's what they want for the table. The units are already there in the table heading, so don't need to write the units down here. And then for the graph utility, you have to click on this icon. How about that? For example, you know, if you didn't click on that icon, you just clicked on graphing. Oh, I guess it does work. At one time I tried this and I typed on graphing and it said no graph is selected. So then I clicked on this icon and then this graph popped up. But you do have to title the graph, please. You can title it something like temperature versus volume. Usually graph titles, if they're just basic like this, it's the y-axis versus the x-axis. The x-axis is usually the thing that you changed, and the y-axis is usually the thing that you watched respond to your change. So in this case, we changed the temperature, so this is degrees Celsius. Temperature in degrees Celsius. It's important to put the units in the axis labels. And on the y-axis, what we watched change by watching the syringe, right, was the volume. And then, unfortunately, you have to copy this data from your data table. Isn't that primitive? You'll notice that we're using Celsius here. You cannot use Celsius when you do gas law calculations, but when you graph, using Celsius can be instructive, and I will show you in a moment how. So here is my very minimal line here. If I click on trend line, then I see the slope and the intercept. Okay, now watch carefully, please. This is not something that I require you to do, but I suggest you try this. At least I don't think I'm requiring you to do this, but I suggest you try this because it's very interesting. Let me make the equation of this line as from your math class, y equals mx plus b, right? Y, the slope is the m, right? So this is 0.830x plus b is the y-intercept, right? 220, let me just round this to 227, all right? 227, okay? So now watch this, folks, watch this. I'm gonna now figure out what would the temperature be if the gas volume were 0? Okay? So what would the temperature be if it was so cold that the gas shrank to a 0 volume? Obviously, as the temperature goes down, the volume goes down. As the temperature goes up, the volume goes up. That's obvious, right? But what if we made it so darn cold that the volume kept on going down, 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 all the way to, this is 220 milliliters, all the way to 0 milliliters. Obviously, that is physically impossible. You can't make matter go to 0 volume in this universe, as far as we know, with the standard model of physics, right? You can't do that, because matter necessarily takes up space, right? All right, so as far as everyday life is concerned, here on this planet, right, matter has to take up space, but theoretically, an ideal gas only takes up space if it has some temperature. So that's why it's called an ideal gas. It's not something that really exists. It's just an idealization, sort of a mathematical model of the way a normal gas would behave under normal conditions. So let's see what happens. So y was the volume, right? Let's say the volume goes to 0, all right? And then let's solve for the temperature, x. So this is the temperature, the x-axis, so this x is the temperature, right? I'm going to solve this for x. Now watch what happens. I subtract 227 on both sides, so it's negative 227 equals 0.830x, right? Now I'm going to divide both sides by 0.830. Okay, and that's going to get me something equals x, right? And I'll do the calculation on the calculator, and I'll put the answer right in that little box. All right. 220. Okay, so that's negative. That's where's the negative sign? Oh well, negative 227 divided by 0.830. So that's negative 227 divided by 0.830. Ooh, look at that! Let me round that to the nearest degree. That's negative 273 degrees Celsius. All right, I'm going to write that down now. Negative 273 equals x, right here. All right, right there. That is hugely significant. Okay, what is x? X is a temperature on the x-axis here. So this is negative 273 degrees Celsius. This is the temperature at which, theoretically, in just a very mathy kind of way, this is the temperature which is low enough to shrink any gas to 0 volume. What is this? Where else have you seen this number? Of course, you have seen this number as the definition of Kelvin. Yes, that's right. This is how scientists came up with the Kelvin scale. They needed a way to measure temperature whereby you would never get to 0. You could get very gosh darn close to 0, but you would never get to 0 in this world. They needed a way to do that. And the reason why they needed a way to do that, or one reason why they needed a way to do that, is because oftentimes when doing calculations with gas laws, you need to divide by temperature. But if you divide by a 0 temperature, you cannot do any further math. Everything stops right there because it's impossible to divide by 0. You can't say 5 divided by 0. There's no answer for that because 0 goes into 5 infinitely many times without ever getting to 5. Of course, you could do 0 divided by 5. That's easy. 5 goes into 0 times. So 0 divided by 5 equals 0. But 5 divided by 0 is impossible. So any number divided by, any volume divided by a temperature which may happen to be 0, this would be the problem stopper right there. You couldn't do any further discovery. So we needed a way to express temperature in a way that will never actually be 0. It may be very close to 0, but not quite 0. And this is the way to do it. We just redefine a temperature scale. We could use the Celsius scale, but say 0 is now at negative 273. You see that? It is impossible to ever get a gas, a real gas, down to a 0 volume. So that means it will be impossible to get the temperature ever down to a 0 Kelvin temperature. So the definition for Kelvin, therefore, is the Celsius plus 273. That makes 0 Kelvin at negative 273 degrees Celsius. That's 0 Kelvin. So this is why when you convert to Kelvin, you just add 273. So now, my calculation here was a little rough. And the scientists in the past found that negative 273.15 is the right number. So that's isn't that interesting? You know, just with the Late Night Lab, you can totally see the origins of the Kelvin scale. By the way, 0 Kelvin, or negative 273 degrees Celsius, that is known as absolute 0. You may have heard that in sci-fi or in the news or something like that. Isn't that fascinating? Okay, now looking at the graph you've created, is volume, so is it proportional? In other words, is there a curve that you could see here? is there a line? A line counts as a curve in math. So if there's a line, then yes, it is proportional. If there is a sliding curve, you know, like this, yes, then that counts as proportional. If it is a up and down curve, you know, like a sine wave, then that is not proportional. Not proportional. And if it is a bunch of points sort of jumbled every which way, you can't really connect them to make a nice sliding curve or a nice sloped line or something. If there's no way to connect the dots, then no, it is not proportional. But in my case, I have a straight line, so yes, it is proportional. And yeah, I guess I'll stop this video